Hello, thanks for coming and welcome to this presentation about scalable online machine learning. First, let me introduce myself. I'm Javier De Matías. I work as data engineer in Trilogic. My company, Trilogic, is an intensive research and development company with specialized in big data and artificial intelligence. We apply these technologies and algorithms in a lot of target industry as banks, telcos, or healthcare or retail. In respect to big data solutions, we can tackle all the types of solutions with big data between, for example, complete data architectures to special use cases with special interest in all the stages of the data, from ingestion to processing or analytics, security. And respect to artificial intelligence, we are ready to obtain the maximum value to the data with special interest in deep learning, reinforcement learning, to get use cases where apply detection problems, classification, something like this. Okay, how is organized my presentation? My presentation is organized. First, I go to introduce what is scalable online machine learning and why we think is very interesting now. Secondly, I will introduce what is Soma Library and how can use this type of problems. And finally, I will show an industrial use case where we apply this library and this type of solution. Okay, what is scalable online machine learning? Scalable online machine learning is the idea. The main idea goes with the confluence of two important trends now. First, data stream processing, that is very interesting now, and the integration with machine learning, that is the main solution to most of the data analytic problems. Respect to stream processing, we have this set of good friends to implement solutions. We have data stream processing frameworks to implement application. We have solutions to integrate different components like Kafka or RabbitMQ. We can implement jobs with Flink, Storm, Spark. All people think that is a good trend now because companies need to process in real time or near real time. But there are a problem when we had to integrate machine learning in the data pipelines, in data stream processing pipelines. When we can find a solution to that, the classical solution of the main important solution is to divide the data workflows in two circuits. One circuit to create a machine learning model. We store historical data. We can train a new machine learning model, test if the model is good or not, or is suitable. And when we decide that this model is suitable, we deploy it in the other circuit where this machine learning model is used, for example, to make predictions or classifications. This type of solution is the solution that we find when we search, for example, in Google, how solve it. For example, if I Google this topic a month ago, and I find some figures with the same solution. For example, this is an Azure solution, which we have a data lake where we store events of sensors. And with this historical data, I train the model and deploy in the string analytics. Or this other with MapR. We have stream processing, a batch processing. The batch processing stores the historical data. With this historical data, we train the model. And finally, when the model is suitable for use in production, we deploy in streaming processing. This is we can talk about a classical solution, but this is not totally good. We can find problems with this type of solutions. First of all, I had to develop two different data workflows with common points, but different. As I explained before, we have a training data workflow and a prediction data workflow. The prediction or exploiting the machine learning model. This makes that we have to build more complex architectures. And maybe these more complex architectures gives us more points of failure. And the most important thing, we don't have the most up-to-date model possible. If, for example, I decide to train my machine learning model with the events produced or collected during the last month, and there are changes in my during this month, maybe I have a good machine learning model, but it's not totally ready to detect some problems that there are in the data trends now. We can make short the time to train and deploy the model, but I always have an old version of the most updated model possible. Okay, this is the drawbacks of the classical solution, but how we can solve it, or what is the idea of scalable online machine learning? The idea is to train and predict at the same time, and in the same solution, in the same data workflow. In this way, we have a unique data workflow with less points of failure. The data architecture that we propose is simpler, and the most important thing, we have the most up-to-date model possible in each occasion. We have the best model to totally adapted to the changes in the data trends. It seems to be a good idea, but what happened is difficult to implement something like this. It's very difficult because we have two important challenges. First of all, I have a challenge respect to machine learning algorithms. Not all the algorithms are suitable because there are some algorithms that need to process all the samples of the data set at the same time. And this algorithm is not totally suitable to use on this way. And the other thing, I could find algorithms which are suitable to be adapted to this processing way, but we have to adapt it because these machine learning algorithms have to be ready to only process each data only once. And maybe we can find a lot of algorithms, but have to be ready to use on this way. The other challenge is a technical challenge. This is an example of Flink cluster, how a Flink application is executed in a cluster. The job manager receives a task and parallelize the tasks or the job between the different task managers, 3 task managers in this case. The problem is where the task managers, for example, have to train the machine learning model, but where is this machine learning model stored? Because all the task managers need to access to this machine learning model, and needs to be able to update this machine learning model. This challenge or this component that we can find to solve this problem is parameter server. A parameter server is a piece of or a component of the architecture where we can store the machine learning model and with a communication between the workers. The Spark workers, for example, is a Spark cluster, or communication with the task managers is a Flink solution. This parameter server can solve the problem. Once we know what is scalable online machine learning and how the challenge that we need to to tackle, I will show as a library that try to solve this problem, this Soma library. Soma Library is an open source library with of online machine learning algorithms. It's open source. It was coded during the development of a European research project. It contains two important things. First, a collection of online machine learning algorithms, and a set of abstractions to make easy to develop new algorithms with this premise. Soma have algorithms adapted to this paradigm. But how solve the problem of parameter server? Solve this problem with a project, an open source project called Flink Parameter Server. Flink Parameter Server is an abstraction for the model parallel machine learning model, and it could be used, it could be integrated in a Flink job. This solution is a solution that we can integrate in the Flink streaming API. How works Flink Parameter Server? Flink Parameter servers have a communication between respect to the workers. The workers have an input data stream and output data stream, and during the processing of the worker, maybe the needs to access to the machine learning model. There are two operations to communicate between the parameter server and the worker. If we need to recover the most updated version of the model, we make a pull operation to obtain the model. If we have a most updated version, for example, in the training step, if we get a most updated version of the model, we have to make a push operation to update the machine learning model stored in the parameter server. The communication between the worker and the parameter server is asynchronous. We can make a pull operation to request the model, but only we have to wait until we receive the answer pull to obtain really the model. Is the working and the communication. For example, if the worker receives new label data to train the model, the worker has to pull the model to the parameter server, wait until receive the answer pull, and finally train with the new data, train this model, and when this new version of the model is obtained, push to the parameter server to be ready for the other workers. This is the main working. This is the interface between the workers and the parameter server, but how we implement the relation with parameter server? We had only to implement two things. What we do when we receive data, we implement the method onReceive. When I receive new data, how my work works, and what we do when I receive the machine learning model from the parameter server. It's like a callback. With these two implementations, we can interact. We can implement interaction between the worker and the parameter server. And Soma, as explained in the other slide, Soma is prepared, is ready to add new algorithms that have abstractions to make easy this works. How is the implementation of a new machine learning, of online machine learning algorithms with Soma? You only have to implement two things. The method delta is to implement what we do when we receive new level data. We update how I update the lasso model, for example, in this case, and predict what we do, how we do the prediction with the model. With only these two things, is implementing a new algorithms in the library. All the rest of the necessary implementation is included in the abstraction and the implementation of Soma. It's very easy to introduce new algorithms because we only have to think how to train the model and predict the model with only one sample. Okay, this is the Soma library. And we know what is scalable line machine learning, the Soma library. Maybe it's the time to talk about a use case where we have applied this technology. I will talk about an industrial use case. It's about steel making. Steel makers make a lot of types of products. Different final products are very different. We can use steel to car manufacturers, to a turbine or a cable. In this case, we talk about produce a steel coil. What is a steel coil? In a simple language, a steel coil is a very long and thin piece of steel roll up. It's something like this roll. It's a very big roll of steel. How is the production of a steel coil? We have in the beginning a big block of steel, and after a processing of temperature and pressure, we obtain the final steel coil of a thin layer of steel. What's the key in the production? The key in the production of steel coil is the flatness. It's very important that the final product have enough flatness to be suitable for the purpose that it was made. The idea of this problem is we have a data stream processing problem where we receive data of the sensors that is measured during the production of the steel coil, and we have to predict if the final steel coil will be flatness or as flat as is needed to the final purpose. The problem is that we only note the real flatness in the steel coil when the 2 or 3 minutes after the steel coil is produced. And it's a problem because the maker needs to know before to maybe stop the production or to downgrade the quality of the steel. Other problem is that we receive fragmented data. We only receive the data of a sensor at a time. We not receive all the data in the same period of time. We receive during the processing of the steel coil, we receive a lot of events of data. The events that we receive have this format. We know what is the coil ID, the identifier of the coil. It's only to identify to know what is the number to number the coil. Bar ID, that the identifier of the variable that the observer variable. This variable could be a variable of temperature, pressure, or other important magnitude during the processing. The value, what is the value of this variable of the coil, and what is the coordinate, where the coordinate is the position of this measurement in the complete piece of steel. How we receive the data in the problem? The problem, we receive the data in 2 Kafka topics. One of them have the information of these measurements of the sensors, and other have the measure of flatness at the end, with a delay respect to these real-time measurements. Okay, this is the input data. who is the expected output data? It's very simple. We expect to know an early prediction of the flatness in the final piece of steel, because it's not possible to know during the processing. And the global or the final solution will be an application, in this case a Flink job, who receives 2 topics, one for the sensor measurements and other for the flatness measurements, and produce in another Kafka topic a flatness prediction. This flatness prediction will be read for operator in the factory, and he could decide if this steel coil would be good or not, or maybe if the steel coil will be at the best quality, or maybe 2 or 3 grades less than this best grade of quality. Okay, this is the idea, but how works the application? As I explained before, the data is fragmented. Why? Because between the starting of production of the coil and the end of production, we receive a lot of event measurements. And in each, for example, as we can see in this chronogram, you will receive from sensor 1, the variable 1, in the x coordinate 5, a value of 14.3 of this value. Or we receive the different sensor information in different times during the processing. And only after the coil was end, we receive the flatness measurements, the real flatness measurement. This real flatness measurement is the information that we need to know if I would predict or not well. Where we predict and where we train the model. In each time that we receive an input event, I make a prediction. With this value of a variable in a position, we need to know how we will the flatness. When I train the model? I train the model when I have all the information at the end. At the end, I receive the real flatness values, and with these values, I can train with all the events of the received during the coil production. We have to take into account that we need enough memory to store the input events before receive the final flatness, because we need to label these input measurements with the real flatness values. When we have this information labeled, we can train the model and update it in the parameter server. This is how the application works, and what's the results of this application. The result is this is a comparison. This figure is a comparison between the prediction of our prediction, which is the top figure, and the real flatness measurement in the bottom of the picture. In a detail, we can see that we can not detect the absolute value of the flatness, but we can detect the data trends changes in the measure of flatness. It's maybe it's not enough to get an absolute value, but it's enough to the operator to decide if the coil is good or not, and what is the data quality of the steel quality of the final coil. Okay, this is the results of the solution. What the conclusion about this technique? Our conclusion is that machine learning in data streaming application is totally integrated, and there are a lot of solutions now to use it. But and scalable online machine learning could be a good solution because it's a promising solution and it seems to be good to use. The problem now is that we have an important piece in this architecture that is parameter server, but the parameter server solution that we can find now has to evolve and to integrate better in the data processing frameworks. Today, we have solutions like Flink Parameter Server or other solutions to Spark, but are not enough mature. In the future, maybe it's necessary to find technologies to implement it with a best performance and better adapted to all the possibilities that we can find in this type of problems. For example, Flink Parameter Server is an open source project. It's very interesting, but it's supported only for 2 or 3 open source contributors. And they did in the GitHub repository. You can use it, but it's an experimental solution. For example, the industrial use case that I have explained is only a prototype because it's very difficult to deploy it in a production environment. Maybe when we can find a mature solution for parameter server, we can obtain a good solution for this type of scalable online machine learning algorithms. OK, that's all. Thank you very much for your attention, and I wait your questions.
And I have heard that parameter servers can be slow sometimes because when you have a lot of parameters to deploy, there is a lot of traffic in the cluster. So have you feel this performance issue?
Yes, this is the main problem in the parameter server because this communication between the workers and the parameter server maybe can have a problem when you have a lot of traffic between them. This is the one of the reasons because this is an experimental solution because you can find problems when you have a lot of traffic. Maybe you have included problems of deadlocks because it's an asynchronous communication and maybe the parameter server is waiting to receive an answer for the worker, and the worker is waiting something for parameter server, and you can find a deadlock. This is one of the reasons it is an experimental solution. OK, more questions? Thank you very much.